So this is okay. So this is an extension to some work by Adam Callison, who looked at single stage quantum walks, trying to solve the same sort of problems. So just start with some definitions. So the problems we're going to be solving are Ising problems, where we choose these coupling parameters from, well, we sample them from a standard normal distribution. I'm going to write it in this form where there's no local fields present, so we only have coupling parameters. The two formulations are equivalent, so we can fix one of the spins. Let's say the last one gets fixed as spin up, and then that defines what the local fields should be. And we get this kind of formulation. But you can go the other way as well and take this kind of problem, introduce an extra spin, and then couple everything together to remove the need for local fields. So this form is going to be enough for our needs. And it makes some of the calculations a bit simpler later in the presentation. So for the driver Hamiltonian, we're going to be using just a sigma x gate on every qubit. This is also what I call the graph Hamiltonian because it corresponds to the adjacency matrix of the hypercube graph, or the n-dimensional hypercube. So because we're doing quantum walks, it's a bit more of a geometric way to think about it. For numerical calculation later, it's useful to have this recursive definition at the bottom. And essentially, what this shows us is when you apply Hg to a vector, the operation you get looks something like a Fourier transform in terms of how you actually calculate it, which again comes in handy later. So what is a quantum walk? We start in the ground state of our graph Hamiltonian, which is just the uniform superposition, and we want to end in the ground state of our problem Hamiltonian. Now, in a quantum anneal, for example, you'd evolve under Hg, and then you'd slowly you'd ramp up the Hg Hamiltonian, no, ramp down, sorry, and ramp up the problem Hamiltonian, so that in the end you're evolving just under the problem Hamiltonian. In a quantum walk, however, we instead pick a fixed Hamiltonian somewhere in the middle and just evolve under that. So it's time independent. Because it's time independent, we're able to just write down the solution to the time dependent Schrodinger equation. And it's just the matrix exponential pretty much. A quick note on this alpha and this beta. So these are essentially free parameters. However, what we mostly care about is the ratio between them, which I'm defining as gamma. This does absorb this factor of alpha into the time taken. And when we're discussing implementation on physical hardware, we do have to care what alpha and beta are. But for the sake of this, and if we look at something such as D-wave, the actual restriction ends up that alpha is proportional to log of n, so log of little n, the number of qubits. So it's not a big factor. It's not something we really need to worry about. So then a multi-stage quantum walk is something in between a regular quantum walk and a quantum anneal. So we still have the same idea of evolving under a fixed Hamiltonian. However, we now do this multiple times with multiple Hamiltonians. So we now have, I usually use the letter M, so there's M stages, and now we have M sets of these parameters, so gamma and T. And then we just evolve under each of them and get our final state. So this is more of a graphical way to look at it. So as our anneal progress goes from 0 to 1, we can see in the quantum walk, gamma is just constant. For the multi-stage quantum walk, it's piecewise constant. So at any given point, it's constant, except where there's a discontinuity. And this gives us the easy calculation, but also it gives us a different route to the solution compared to quantum annealing, because in quantum annealing we have the adiabatic theory, which essentially acts as like a speed limit, saying you can't go faster than this and be guaranteed the solution. But we don't run into that problem with multi-stage quantum walks unless we take the limit where this starts looking like an anneal. So as the number of stages goes to infinity. So we have a lot of free parameters in this method. So for each stage, we have the gamma and we have the time, and we'd like a way to pick those that doesn't involve a lot of like classical iterations like you would do in QAOA typically. So to begin with, we're going to look at something that Adam Callison derived in his paper for single stage quantum walks, which is the infinite time average. So this lets us ignore T for now, and it can give us a good indication of what gamma we'd like to choose. So essentially we define this average, so we're just averaging over the probability and then dividing over the time that well, integrating over the time, then dividing by the total time. And when you take this limit, you get this formulation here. So this looks like a projection into like this intermediate state. This intermediate state is these are the eigenvalues, sorry, eigenvectors of the Hamiltonian we're evolving under, so of our H. So the way that I think about this is you're essentially projecting into this intermediate state and then projecting onto your final state. And so we're kind of slotting in the state that we're trying to slot in a state that's in the middle of the two so that we get the best result. So I think about it like if you've got three polarizers, this A is representing our ground state Hamiltonian, the B is representing our our problem Hamiltonian, and we're trying to slot in our own Hamiltonian that will get us as much as the chance of getting the ground state as possible. So ideally, we'd want this 45-degree angle here, which does sort of correspond to a 45-degree angle between these vectors in the vector space of solutions. Then as we move to the multi-stage quantum walk, it turns out we can extend this definition where now we're integrating over multiple time steps because we now have a time step for each stage. But we get very similar expression at the end. So we start in the ground state, we project onto the ground state of the first Hamiltonian, then onto the second one, and then the third one, and so on until we get to the problem Hamiltonian. I said ground state, but this sum is actually over all of the states. But the ground state is like the one you expect to be most important here, because we're hoping that we stay in the ground state all the way through to the end. We don't, of course, but that would be ideal. So it's worth mentioning that we can actually calculate this reasonably for small problem sizes. So even though it looks like a multi-dimensional sum over every stage, we can actually rewrite it in this formulation where it just becomes a series of matrix multiplications, essentially. So the inner part here is a matrix that's diagonal in the basis, in the eigenbasis of the first Hamiltonian we evolve under. So you can rotate into that basis, write it down, and then we do the same thing for the second Hamiltonian. Rotate into that basis, write it down. So it is still computationally heavy, but it only grows linearly with the number of stages. So we can actually use it. However, the idea of trying to place Hamiltonians so that we can rotate from the first stage to from the ground state, from the ground state of the graph Hamiltonian to the ground state of the problem Hamiltonian gives us this idea of, well, literally doing a rotation, treating these as if they're vectors. So they need to be properly more normalized, which we'll discuss in a moment. But the rest of this is just rotation. And this gives us effectively the gammas that we want to choose for each stage. So to normalize, we want these two Hamiltonians to have the same energy spread or spectral norm, if you want to use the mathematical term. Um, for the graph Hamiltonian, this is simple as it's exactly known to be 2n. For the problem Hamiltonian, this is more difficult because if we if we knew the exact value, that would be equivalent to solving the problem. However, there's some ways to estimate it. So again, in Adam Callison's paper, he had this expression to calculate or to estimate the average. Um, this essentially comes from assuming the energy levels are distributed as a normal distribution, and then we use extreme value statistics to estimate what the largest one should be. And then you multiply by 2 because the smallest one should be the same magnitude but negative. However, there's a multiplicative factor of 0.887 that he introduces to correct for the fact that the distribution isn't normal. Um, However, in my work, it seems that this is a small scale effect that disappears for larger problems. So I don't use this extra factor. The advantage of One of the advantages of this method is that it's not too sensitive to the choices of parameters. So the difference between the two isn't actually uh, noticeable, really. So now we want to stop working with infinite time because we can't actually evolve anything for infinite time. So we're going to look at what short time values might be reasonable. To start with, I took the energy in the graph Hamiltonian, which we know starts at a minimum of minus n. And we want to see how this evolves just by taking a Taylor expansion and seeing what expression we get. What I'm doing here is we take the lowest order that isn't 0, and then we see when this predicts a non-physical value. So as I said, we know the spectral radius of this is exactly minus n to n, so 2n in total. What this gives us is strict bounds on what energy levels are allowed. So when this predicts something greater than n, we know that higher order terms must have come into effect and that this quick quadratic growth in energy has stopped. So we get this expression, and if I just skip ahead, we can see here that this works quite well. So the green line is the energy measured in the graph Hamiltonian. The orange line is the energy measured in the problem Hamiltonian, which we want as low as possible. So I've marked on the actual ground state here. And then this blue line is that second order approximation I just wrote down. So we can see it matches at low time scales. However, we can also see that when this predicts a non-physical result, which is what this vertical line is representing, we can see this corresponds really well with where this fast period of decreasing energy ends. So we can see as it flattens out, it matches up very well. So this expression on the bottom, we can actually calculate exactly using a statistical technique where essentially we write down the quantity that we want to find in this summation form, so summing over every possible state. And then what happens is we essentially have to pair up these indices in the sum to ensure that we don't end up with a 0 anywhere. Because if you imagine if one of these s's wasn't paired up, we could flip that spin and get the exact same expression but with a minus sign. So we need these always to be paired up so that flipping one will give you minus 1 squared and remain the same. We also need to make it so that none of the indices in the j's are equal because these are 0 along the diagonal by our definition. So if you work through with these restrictions, you're often able to write down a formula for what these statistics should be, which is easily calculatable from the J matrices. So in this case, it's just an element-wise square summed over. And so we can do the same thing for this expression here. And what we end up with on this denominator is actually this same expression, but with a 4 in the front instead of a 2. So we can now compare this to other results in the field. So this is some work by Robert Banks, where he shows that you get, or you can't have sampling shorter than this t to the minus a quarter. And if we look at his expression, so we're using a complete graph here. So k squared is the number of edges, which looks like n squared. So we can see here there's a form k2 squared, or kappa, I think that's kappa. Yeah, kappa 2 squared. So we get this t is roughly equivalent to n to the 4. And so when we do t to the minus a quarter, we have t to the minus, n to the minus 1, sorry. So this formula that I have ends up looking like n to the minus a half. So it's not an unrealistic time when you're comparing it to this. However, it does disagree with what Adam Callison found, which was approximately n to the half. But the way he calculated it was to instead successively increase the time evolving under until it's within 5% of the infinite time average. So I'm not trying to match the infinite time average here, but rather just find this is sort of the shortest reasonable time to evolve under. So I already showed this graph. When we then do a multi-stage quantum walk, what I'm doing currently is just using the same time step for every single stage. So the calculation we did actually only holds for the first stage, but we're hoping that it holds for every stage because after the first stage, we no longer know what state we're in. And so unless we want to start making some assumptions that we are still in the ground state or something, then there's not a lot that we can do. However, this does seem to work well. And in fact, we can possibly shorten this by a factor of, I think it's square root of m, so the number of stages. Because what I was assuming is that we're going from the lowest possible energy to the highest possible energy. But for a multi-stage walk, we're getting there in m steps. So we're actually only going to go from like -10 to 1/5 of the way. So we'd expect to get to like -6. We don't even make it that far. So now for the actual results. So here are results calculated across 2,000 instances of spin glass problems for each point here. And we're going to use the infinite time average at the moment. So we can see that for a given number of stages, we get a very flat looking line as we increase the number of spins. So the y-axis is logarithmic. So the problems do scale exponentially. But what we see is that as we increase the number of stages, we decrease the how steep the scaling is. And when we look at the short time average, we get a very similar result. So it's not as flat, both in terms of the actual gradient of the line and also how close the line is to being straight. But we still get the same idea. As we add more stages, we get a flatter line. Something that I haven't been able to explain yet is there seems to be this like oscillatory pattern as you go from even to odd numbers. So you can see it decreases slightly for an even number and then increases. It's only very slight, but I'm not certain why that is. Um, the only thing I've noticed is that the graph Hamiltonian is not a full rank for the even numbers. So I wonder if that's somehow preventing the system from evolving quite as effectively. But it's a very subtle effect. So my old results showed this graph that essentially shows that as we increase the number of stages, we can reduce the scaling exponent as much as we like, pretty much. This was looking like a polynomial relation. However, I now have some new results by using a dataset provided by Tim Boda. And his dataset is problems that have been curated to specifically have very small energy gaps. And as a result, are difficult for quantum computers to solve. So when we look at his problems, so there's only, well, the number of these is inconsistent, so it's no longer 2000 per point. I think it's about 100 for the last set, but about 2000 for the first set. So it decreases as we go to higher sizes. Um, but now we get a fairly similar result, where as we increase the number of stages, we get a flatter line. However, we now see we eventually hit a wall where adding more stages decreases the success probability. So as we go from 10 to 20 stages, it's a bit hard to see, but I hope illustrates the point. Um, something worth adding. So if we look at these short time averages, the scaling for the one stage line is like 2 to the power of 0.4. Is that right? Minus 0.4, sorry. And the scaling for the top ones, 20 stages, is something like 2 to the power of minus 0.06. So the first one matches with what Adam Callison found, but we can see that as we go to enough stages, we can get quite good scaling that matches the best classically known algorithms. So I think the best known algorithm is 2 to the power of minus 0.2. I would have to double check that. But there's a paper from Ashley Montanaro who looks into it. However, what we see is that this might not be completely accurate, at least for this set of results. Because if we look at the 10-stage result here, it gives us scaling of like 2 to the power of minus 0.07. So somehow 10 stages on the hard problems is almost as good as 20 stages on the easy ones. So I think these are like artificially flatter than they should be. But we still get the effect that if we look at a column, that as you increase the number of stages up to a point, you get a better chance of success. And it seems like if you go to a high enough number of spins, eventually using more stages becomes viable. So I just wanted to make a quick note on some numerical methods that came up in this work. So we have to calculate this matrix exponential. Now, typically in software, for example, in SciPy in Python, the technique used here is to use a Taylor expansion and just evaluate as many times as you need to reach some specified level of accuracy. However, we can actually do better than that. So there's two factors here that mean we can do better. Firstly, we know the bounds, or we can calculate a bound on the energy values. So we can just measure the L1 norm, for example, of the matrix, which is easy enough to do. Once we have the L1 norm, we now have bounds on the magnitude of the eigenvalues. However, because it's Hermitian, we also know they're real valued. So what we actually need is to find a polynomial that is accurate for every eigenvalue, which we know is real and bounded. And the Taylor polynomial is not the best choice here. So if we didn't know they were real, then the Taylor polynomial is the best choice. But what we can actually do is, if we wanted, we could solve what's called the minimax problem, which would give us the actual best polynomial. But this is quite difficult classically. So what I do is use Chebyshev polynomials, which are a very close approximation. Um, and there's two advantages of this. Firstly, they um, converge much faster, so we need less iterations or less terms of it. And secondly, they're more numerically stable. So in the Taylor expansion method, you end up having to only do, well, you have to do a small Taylor expansion repeatedly. So you can imagine breaking this up into like e to the minus it h over 10 or something, and then you do it 10 times. However, with Chebyshev polynomials, you don't have to do that at all. You can just do one huge Chebyshev polynomial, and you get better accuracy and you get better speed. So in summary, multi-stage quantum walks provide better scaling with more stages up to a point. For the easy problems, I wasn't able to scale it far enough to see what that point is. But for the hard problems, we run into a wall eventually. The large number of parameters that appear can be effectively chosen. So the gamma parameters and the t parameters. And these heuristics that I showed work for any problem. I've only tried them for spin glasses, but the theory should hold for any problem, especially for the t parameters, because those are calculated directly from the J matrix. So a problem with this is that realistic hardware implementation is unclear. So if we go back to where I say what t is here, so there's a missing factor of 1 over alpha here, which I said earlier. And on something like D-Wave, alpha is something like 10 gigahertz. So we end up with timescales of like, I think that's 100 picoseconds. And then we end up with a factor that looks like n to the minus a half. So if we had like a 100 qubit problem, we're looking at 10 picoseconds we have to evolve for. And from my understanding, there's not a lot of current hardware, or at least on D-Wave, which is what I'm most familiar with. You can only do anneals that are, I think 500 picoseconds is the shortest they do, which is quite a new feature as well. So how we could implement this is not 100% clear. Plus, we have to worry about minor embedding, and then how does that affect the time scaling and all that kind of stuff. I haven't looked at other problem types, so I don't know if the same kind of scaling exists. And also, these simulations are very sort of optimal or unrealistic in the sense that there's no noise being simulated and the quenches are instantaneous. So, because these are so short, the noise probably isn't much of an issue. But the fact that we assume the quenches are instant is because, again, something like D-Wave can only ramp up and down the Hamiltonians so quickly, and the timescales it does that are on the same order of the timescales we're evolving for. So there's a link to my GitHub where the code for this project is. And thank you. Are there any questions?
Thank you, Isa. So any questions or comments? So I do have a question. So I understand it's not realistic to conduct on D-Wave, current D-Wave system. But as you mentioned that this algorithm, something between the QA, OA, and D-Wave. So do you think the many people implement in a gate-based the computer or the various QA/OA type of algorithm? Do you think you can implement your algorithm on quantum gate hardware like IBM or other providers?
Yes. So if we just take a look at the definition, there we go. So what it is possible to do is interpret this as a QAOA scheme. So we can apply trotterization to each of these matrices. Let's say you want 10th order trotterization or something. You'd end up replacing each of these stages with 10 stages of QAOA. And then the parameters for QAOA have already been decided by the parameter choices for this. And if you go to a high enough order of trotterization, you should get effectively the same results. So yes, and we are looking into what other hardware we can try and implement this on. But D-Wave's just what I'm most familiar with at the moment.
I see. So current cutting edge hardwares like ion trap as well as the IBM, the superconducting qubit hardware, their quality is getting good now. So I think it's now it's time to think about it. It's worth to think about it. I think. Thank you.
Thank you. So we do have a neutral atom quantum computer here at Strathclyde. So I think one of the next steps is to talk to them and see if I can try getting it running on there.
Okay. Any other questions? Okay. So thank you, sir, for great presentation.
Thank you.
And I'd like to close this seminar. Thank you. Have a good day.